Hi everyone, welcome back to the course Manufacturing Process. Today we are going to discuss about wire drawing in first part, and the second part we are going to discuss about sheet metal working. Wire drawing is a common process in manufacturing to produce wires, bars, rods, etc. So tensile stress is applied to produce wires. So the course learning outcome is describe a metal forming process called wire drawing and compute process dynamics and performance. Apply engineering calculations on wire drawing process. Now here, wire and bar drawing. Cross section of a bar, rod or wire is reduced by pulling it through a die opening. This process is called wire drawing process. So pulling the material through a die opening. Pulling means applying tensile stress so that the material will get pulled through a die opening to produce a wire, a rod or a bar. That is called a wire or bar drawing process. It is somewhat similar to extrusion, except work is pulled through a die in drawing operation. Although drawing applies tensile stress, there is a significant impact of compression also. So the material will get squeezed or compressed between the die and the surface. So material will undergo plastic deformation, it will get squeezed and then it will get deformed to a wire or a bar or whatever it is. So what are the mechanics of wire and bar drawing process? The starting stock, normally it's a rod, for example diameter D0. It is passed through a die which has an angle alpha, and the material is pulled from the other side. That's why tensile stress is applied. D0, initial diameter. When it gets squeezed through the die opening, its diameter will decrease and will get converted to or deformed to a final diameter df. The contact length during the process can be taken as LC, which is the contact length. So what is the mechanics here is, when we pull the material through a die opening, when we apply a tensile stress or a force F through the when we pull it on the other side, the material will get squeezed inside the die. Material will get compressed inside the die. Material will undergo plastic deformation, will deform to a final shape as like a rod or a wire or a bar. Normally circular wires or bars or rods are produced. Now you can see here the forces, which material is best for drawing, wire drawing operation. Gold is the most ductile metal that exists for drawing operation, or we can say the most ductile material is gold. If you take 4 pounds of gold, that can drawn into a wire that stretches across the country. You can see here that can be used, that can be like you can stretch it to a dimension reaching from one end of the country to the other end of the country. Mechanics of phenomenon: there is a tensile stress which is due to pulling force, but compression also will come into act. The material will get squeezed down as it passes through the die opening. If you see here, the tensile stress is applied in here and it will be acting here to pull the material. In addition to that, there is a compression stress which acts within the die itself, between the material and the die, the compressive stress, and so that the material will be squeezed. What parameters we need to study? The parameters are area reduction R. Initial area is taken as A0, final area is AF. The draft is initial diameter minus final diameter. So if you look at the different parameters of a drawing operation, initial diameter is D0 and final is DF. The contact length is taken as LC and the force applied is F. The angle of the die is taken as alpha. If these are the parameters, you can see here initial diameter, final diameter, die angle, then contact length, friction between the material and the die, and the force applied. So the area reduction can be calculated as initial area minus final area divided by initial area. Now different parameters, how to calculate different parameters, how to reach different parameters. The strain can be calculated as log A0 by AF, initial area by final area, which can be calculated as log 1 divided by 1 minus R. R is the area reduction, A0 over AF. The stress that results from this ideal deformation, as I explained, this is strain without any friction. We don't consider any friction in the material between the material and the die. In that case, the strain, ideal strain, we say that the ideal strain can be calculated as log A0 over F. Stress can be calculated as flow stress times strain. Flow stress is YF times log strain is A0 over F. Flow stress can be calculated as K epsilon raised to n over 1 plus n. K is the strength coefficient, epsilon is the strain, n is the strain hardening coefficient. Using this we get a flow stress and then substitute here to find the resultant stress acting the wire drawing process. The drawing stress is calculated. How much stress? We are using a force F for pulling the material out of the die opening. If F is the force, then how to calculate the drawing stress? The drawing stress can be calculated as flow stress times 1 plus mu over tan alpha. Mu is the frictional coefficient, alpha is the die opening, times phi is a inhomogeneous deformation factor, times log A0 over F, initial and final area ratios. Phi is inhomogeneous deformation, which is 0.88 plus 0.12 times d over LC, where d is the average diameter of the work. Average diameter means initial plus final by 2, and we have phi, inhomogeneous deformation, can be calculated by 0.88 plus 0.12 times d over LC. The contact length can be calculated as initial diameter minus final diameter divided by 2 sine angle of the die open. Now the drawing force can be calculated using the equation. Force is area times stress, final area times drawing stress. Using this equation we can find the drawing force, which is AF y bar, which is actually the flow stress times 1 plus mu over tan alpha times phi, inhomogeneous factor times log A0 over AF. Now what is the difference between wire drawing and bar drawing? Wire drawing is basically for producing small diameter stocks, wire sizes ranging from 0.03 millimeter, that is called wire drawing. But bar drawing means normally it is for larger diameter bar and rod stocks. Although the mechanisms are same, the mechanisms like pulling and pulling from one side and the material gets squeezed in the die opening, but the equipments required for these two operations are different. So the drawing practice itself is different. Usually the bar drawing or wire drawing, they are done under cold condition, cold working process, most frequently used for round cross sections. Cold working, the strength and finishing will be much better than the hot working process. So what kind of products we can produce using wire drawing and bar drawing? We can produce electrical wires, wire stock for fences, coat hangers and shopping carts. So using rod stocks we can produce nails, screws, rivets, springs, etc. Bar stocks can be used for producing metal bars for machining, forging and other processes. Now bar drawing, as I explained, comparatively larger stock. It is pulled from one side, material gets squeezed and we get a rod or bar, etc. If we need a hollow rod or a section, then we have to go for a mandrel. When we use a mandrel, the product produced will be hollow. So bar drawing bench, as you could see here, normally operated by hydraulic, and then there are pistons and piston rods which is connected to the die. So as you can see here, it is pulled from one end with the help of hydraulic cylinder. It is pulled from one end, and the drawn bars will come out through the die. This is the die. As you could see, the starting material is fed through from this side, and these are the drawn bars. It is pulled by a ram or a carriage. You can see here, this is a ram or a carriage. Using this ram or a carriage, which is operated by hydraulic force or hydraulic cylinders, the ram which is fixed to the bars, it will pull the bars out of the die, and we get the final finished product. So this is the starting material, and this is the final finished product. Now wire drawing, it's continuous drawing process. As you can see, minimum 4 to 12 separated dies will be there, multiple dies will be there. As you could see here, in the first die there will be a small reduction in the first step, and then again there will be second stage reduction, there will be third stage reduction. So after several reduction, we get the final finished dimension of a wire. So it's a continuous operation consisting of multiple dies, normally 4 to 12, and there is a drum which is rotating continuously. This will feed the force. The drawing force is given by the drum or capstan. Proper force to draw wire stock through the upstream die. The pulling force is given by the drum which is rotating continuously. Sometimes annealing is required between the dies to relieve the work hardening efforts. Now what are the features of a die? The features of a die are entry section, then approach, then we have a bearing surface and a back relief. Entry section means the portion where the material enters the die initially, where friction will be more, so lubricants need to be applied at that point. Approach is the cone shaped plane where friction takes place. More friction will be acting where the plastic deformation of the material takes place. Material will get squeezed in the approach section, and the diameter will get changed, or the material will get deformed towards a final shape in the approach section. Bearing surface determines the final dimension by a final diameter. Back relief is the exit zone where the material comes out of the die. The normal angle given is 30 degree. Normally the die materials are produced by tools, steels and cemented carbides. Here there is an example, a wire to be drawn. The angle alpha is given 15 degree, initial diameter d naught 2.5 mm, final diameter df 2 mm. The coefficient of friction mu 0.07, strength coefficient K given, strain hardening exponent N given. Determine the drawing stress. First of all, we need to find the inhomogeneous factor, which is phi equal to 0.88, as I explained before, plus 0.12 times the initial diameter 2.25 divided by contact length, which is given as 1 mm. So using this, so we have phi, we can calculate the drawing stress. Before that, we need to find the strain. Strain is log initial area by final area. Initial area can be calculated from initial diameter, and final area can be calculated from the final diameter, which is 2 mm. So using initial area and final area, we get a strain which is log A naught by AF. Then after that, we get flow stress K epsilon raised to N over N. K is given, epsilon we calculated from here, N is given, we get the flow stress. After getting flow stress, we can calculate drawing stress using the equation. And then finally, the drawing force is the area, final area times drawing stress. Using that, we can find the final the required force of drawing required for the drawing process. Thank you.